Here's a satellite that hangs motionless in the sky. Point a dish at it once, and you never move the dish again. How can something orbiting the Earth appear to stand perfectly still? And far out in the galaxy, two stars circle one another with no planet, no ground, nothing at the center at all. Both puzzles fall to a single idea: gravity supplying the inward pull that bends motion into a circle. Let's solve them, one at a time. Our first problem is the geostationary satellite. It circles the Earth once every 23 hours, 56 minutes, and 4 seconds. That interval is one sidereal day, slightly shorter than the 24-hour solar day we set our clocks by. Because its period matches the Earth's turn against the stars, the satellite stays fixed above one point on the ground, which is exactly why a dish can aim at it and never move again. We are given the mass of the Earth, m sub e, equal to 5.98 times 10 to the 24th kilograms. The mean radius of the Earth, r sub e, equal to 6.37 times 10 to the 6 meters, and the gravitational constant g, equal to 6.67 times 10 to the negative 11th. We want the radius of the orbit and how many Earth radii that turns out to be. We model the motion as uniform circular motion. Gravity is the only force acting, and it points from the satellite straight toward the center of the Earth, so the acceleration points radially inward as well. Put the origin at the center of the Earth and let the unit vector r hat point radially outward. Call the orbit radius r sub s, and let omega be the angular velocity, tied to the period by t equals 2 pi over omega. For uniform circular motion, the acceleration is purely radial and inward, with magnitude r sub s times omega squared. As a vector, the acceleration equals negative r sub s omega squared in the r hat direction. Now apply Newton's second law along the radial direction. The only radial force is the Earth's gravitational pull, negative gm sub s m sub e over r sub s squared. Setting force equal to mass times acceleration gives negative gm sub s m sub e over r sub s squared equals negative m sub s omega squared r sub s. Notice that the satellite's own mass, m sub s, appears on both sides, so it cancels. The orbit does not care how heavy the satellite is. Dropping the minus signs and the shared mass, we have gm sub e over r sub s squared equals omega squared r sub s. Multiply both sides by r sub s squared and divide by omega squared, and r sub s cubed equals gm sub e over omega squared. Take the cube root, and r sub s equals the quantity gm sub e over omega squared, all raised to the 1/3 power. Now the numbers. The period is 86,164 seconds, so omega equals 2 pi divided by that, which is 7.2921 times 10 to the negative 5th per second. Substituting omega, g, and m sub e into the cube root gives r sub s equal to 4.22 times 10 to the 7th meters. Dividing by the Earth's radius, that orbit sits at 6.62 Earth radii from the center, which is an altitude of about 36,000 kilometers above the surface. Now a very different setting, a double star system, two stars bound only by their mutual gravity, with nothing at the center. Star 1 has mass m sub 1 and star 2 has mass m sub 2. Each moves in uniform circular motion so that the two stars stay a fixed distance apart, sweeping around counterclockwise. We want the period of the orbit. Because that separation never changes, the line joining the two stars always passes through one fixed point. Each star traces its own circle about this common point. Later in the course, we will name it the center of mass. Put the origin right there. Let r sub 1 be star 1's distance from the center, and r sub 2 be star 2's distance, with unit vectors pointing outward from the center to each star. Since the stars sit on opposite sides of that point, Their separation is simply is equals r sub 1 plus r sub 2. The gravitational force depends on the full distance between the stars, which is as not on the individual radii, so the pull on star 1 has magnitude gm sub 1 m sub 2 over s squared directed inward toward the center. The pull on star 2 has the same magnitude, also directed inward. These are the two forces holding each star in its circle. Let omega be the angular velocity of each star about the center, and here's the key physical fact. Both stars share the same omega, because they stay lined up through the center and complete one revolution together. Apply Newton's second law to star 1 along its radial direction. The inward gravitational force equals its mass times its centripetal acceleration. Negative gm sub 1 m sub 2 over s squared equals negative m sub 1 r sub 1 omega squared. The mass m sub 1 cancels, and the solving for r sub 1 gives r sub 1 equals gm sub 2 over omega squared s squared. Do the same for star 2. Negative gm sub 1 m sub 2 over s squared equals negative m sub 2 r sub 2 omega squared. So r sub 2 equals gm sub 1 over omega squared s squared. Now use the constraint. The separation s equals r sub 1 plus r sub 2, which is gm sub 2 over omega squared s squared plus gm sub 1 over omega squared s squared. Combining the two terms, s equals g times the sum m sub 1 plus m sub 2, all over omega squared s squared, multiplies through by omega squared s squared and divide by s, and omega squared equals g times the sum of the masses over s cubed. So omega equals the square root of g times m sub 1 plus m sub 2, all over s cubed. Finally, the period, t equals 2 pi over omega, becomes t equals the square root of 4 pi squared s cubed over g times the sum of the masses. Look closely at that result. Both masses appear. This is different from the Kepler formula we derived earlier for a small body orbiting the Earth, where only the large mass showed up. That earlier result quietly assumed one mass was far larger than the other, which effectively pins the center point inside the big body. Our two-body formula is the honest version. If we apply it to the Earth and the Moon circling their common center, using their separation of 3.82 times 10 to the 8th meters and the sum of their masses, the period comes out to 2.33 times 10 to the 6 seconds. That is about 14,000 seconds, roughly a sixth of a day, shorter than the estimate that ignored the Moon's mass. Two orbits, one principle. In each problem, gravity alone supplied the inward force, and the Newton's second law along the radial direction did the rest. For the satellite, the answer was a distance. For the double star, it was a period. And notice what the second result quietly taught us. The clean single-body law, where the period leans on just one mass, is really a special case, the limit where one body so outweighs the other, that the center of motion falls inside it. When the two masses are comparable, both of them steer the orbit together. The double star is the honest picture. A planet circling a fixed sun is its convenient shadow. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.